muy buenas tardes, no, buenos días todavía. Un momento, creo que no, ahí está bien. Muy buenos días, muchísimas gracias por venir al seminario de investigadores del Departamento de Oceanografía Física, a los que están aquí presentes en el Auditorio Pedro Ripa y a los que tenemos en las redes sociales. Pues es un gusto que tenemos de invitado al doctor Colin Raymond. Colin hizo un doctorado. I will introduce you in Spanish, if you don't mind. You understand a little bit of Spanish. So. Just a second. El doctor Colin Raymond hizo un doctorado en la Universidad de Columbia y ahora es asistente de investigador en la Universidad de California, Los Ángeles, y también tiene una afiliación secundaria en el Jet Propulsion Lab de la NASA. Su investigación se centra en comprender mejor los sistemas climáticos que interactúan con las características geográficas que producen extremos a escala local y regional, especialmente los extremos de calor, humedad y precipitación. También estudia las secuencias y combinaciones de variables que dan lugar a riesgos sociales o a desastres que conocemos en climatología como compuestos o correlacionados derivados de los extremos climáticos, como lo que nos va a presentar hoy. Y sus intereses también incluyen producir y comunicar información climática en algunos documentos que son importantes para la toma de decisiones y también con conversaciones con las partes interesadas. También le interesan las actividades educativas y de divulgación de la ciencia. Sus proyectos se basan en una variedad de fuentes observacionales y también en simulaciones de modelos globales y regionales. Y quiero resaltar que el doctor Colin es muy productivo, tiene varias publicaciones como primer autor en Nature Climate Change, en Geophysical Research Letters, en Environmental Research Letters and also in Science Advances. De hecho, su artículo como primer autor más citado es de Nature Advances y es sobre the emergence of heat and humidity too severe for human tolerance. So we welcome Colin. Thank you for coming to visit us, and we're happy to hear your talk. Thank you. Well, you can use this one or this one.
Muchas gracias. Thank you very much for that very long introduction. So yeah, I'm happy to be here. Thanks for the invitation to come and meet people and give this presentation and to see Ensenada, which I haven't been to before. Really not that far away from Los Angeles, of course. So, as the title suggests, I will be talking about through the lens of four what I think are pretty interesting examples. I'll talk about this sort of vision that shapes my research about how a combination of physical and societal processes, interactions, lead ultimately to these things that we call compound events or compound hazards or multi-risk. There's a lot of similar terms floating around for essentially the same concept. And then not illustrated in the four examples will be two recent studies that I'm pursuing on the physical side of this. I do come from the physical climate side, as I'm sure most of you do, or all of you do as well. But I guess I try to work with societal experts because of this, I think, a need to recognize how important societal processes of various sorts are for informing and prioritizing the kinds of work that we do. Okay, so I was requested to include a couple overview kind of slides. So as I just said, first I'll survey for disasters of the past, and then I'll, I guess in the last third or so, talk about two recent studies that I've been working on. So the objectives are first to convey this appreciation for the types of ways that societal forces not just shape the impacts. I think we can all think very readily of the kinds of ways that vulnerabilities, for example, affect impacts. But I think, more novel and underappreciated aspect is how those societal vulnerabilities or decisions actually shape the events themselves, the physical hazards. And then, yeah, to talk about two recent physical science studies inspired by this mindset. And so the context, just to give a simple definition of compound events in the climate system, anything, I would say, that has multiple interacting elements that in some way, usually related to the final physical, societal impacts, add up to more than the sum of their parts. So whether that's in space, two things that affect the yields of a crop or something, which affects the global price, maybe two things in short succession in the same place, and so on and so forth. And then incorporating people's decision-making. And I think it's important to note probably that, when we talk about, it's important to be sensitive. And so when we talk about decision-making, people are making decisions, and so we can kind of blame society as a whole, let's say, but I don't want to blame individual people because all of us, including me, are making decisions in the context of the societies that we live. So we sort of set up a zoo for ourselves, right? And then we all are actors within that. So I try to cast the blame, I guess, collectively, right, in terms of failure to adapt or anticipate particular kinds of extreme events. Okay. Our decisions are very important, regardless. Yep. Yeah, and then how to do that, how to take these ideas that I think we know about, we see in the news and so on, and actually apply them to our research is really hard, and I think is beginning to be recognized as important, but yeah, we're still trying to all figure out how. More specifically, right, like what combinations of hazards should we be studying? How do we deal with unprecedented hazards in a particular place or of a particular magnitude, and so on, right? And then, of course, how do we work with people, communicate the results to the people who, like the politicians or nonprofit actors and others who could actually do something about it, or individuals, right? A lot of things can be addressed with sort of small individual changes. So there's 4 examples. So the first one is actually from Italy. So there was a flood that you probably haven't heard of in November 1951, but I actually chose it because I think it is maybe useful in a way to talk about something that we haven't heard of, so we're all sort of on the same page. So this is at the top right is a headline from an Italian newspaper, which you may or may not be able to read, given the similarities of the languages. So the main headline is, "The population abandons Rovigo," which is an Italian city, while water crashes through the city. And then various other, the implacable fury of the Po River. And then there's some photos from the disaster. And then on the bottom left is actually the population of the city of Rovigo from about 1900 to 2000. And the peak is in 1950. So about 100,000 people actually left the city because of the flood and never came back. So what happened in this flood was that, there's a few different things that we can identify distinctly. So first of all, there were some physical drivers that are important. There was a wet summer and a wet fall. Flood happened in November. So that's the preconditioning. Then there was a week-long series of storms. There were 3, I think, distinct storms that came through in the span of a week, which affected multiple tributaries of the river, which are all up in the Alps. And apparently it's quite rare to have storms that cause heavy precipitation in all of those tributaries more or less simultaneously. That's another thing that could be investigated, right, in terms of the probability of that happening and so on. However, on top of that, there were the societal drivers that we can identify. There was the levees built along the Po so that it couldn't flood over its natural floodplain any longer. There was upstream deforestation in the mountains. This is when people were still cutting a lot of trees in the Alps for firewood and so on. So then, of course, when you deforest, then water tends to come more rapidly down the slopes, directly into the river. And then there were different sort of local flood management agencies that were making decisions that were not coordinated with each other. So they sort of weren't recognizing the possibility of a region-wide flood. Each one was concerned with their own tributary. And when when you have a local system, you tend to have a more local and shorter timescale focus, and things don't match up when you're considering the whole system. So the outcomes were the levees failed, like in many other disastrous floods, and people weren't anticipating this in the floodplain. And there weren't a whole lot of deaths, but there were almost 200,000 homes damaged, and that's why 100,000 people never came back. So the context that I put together, this is from a paper a few years ago, the context that I think that I would argue makes sense to try to understand some of this really complex interaction is, I guess, can be broken down into three general categories. There's the setting or the background for an event, there's the event or the disaster itself, and then there's the outcomes and the feedbacks. So I'm not sure how well you can see all of this. What I guess I want to, well, I'll start with the numbered boxes. So box number one is a lot of stuff you can kind of imagine. There's history, governance, finance, that kind of thing. Then there's the exposure and the vulnerability of the population, generally who might be affected. There's the combinations of physical drivers. That's probably what we're most interested in, right, as physical scientists. Then what I did here with the little X's is I actually have updated my thinking about this since I wrote the paper. So when I wrote the paper, obviously I had a line directly from exposure to hazard, but I'm not sure that's true. And what I think is actually more accurate is to have a third box that's specifically the decisions that we have made that affect the environment in some way. So land use, emissions that cause air pollution, building levees, deforestation, sort of land use. I guess you could put, greenhouse gas emissions there too. I don't really include greenhouse gases just because they're sort of in the back of everything, so it's not so interesting maybe to talk about them all the time. But I guess you could put greenhouse gases there as well. Anyway, so I would say that the physical drivers and the environmental decisions that we've made combine, generally speaking, to create hazards. Those hazards have impacts, those impacts have responses, and the response sort of feeds back onto just about everything else. So I guess the key point is that the environmental decisions that we make can really act as a multiplicative element in increasing the severity of the hazards that then have these impacts and so on. And they also, I think, affect the feedbacks and our ability to adapt in a reasonable way to everything, as opposed to not trying to, as opposed to not taking into account all of the evidence as we might otherwise. So I like this quote from Proust because I think it kind of captures that we see this all around us, but we don't often crystallize it in this way. So just to put the Italian flood on this framework, right? We have in the background on the left, we have these kind of local flood management approaches. We have a state that was still recovering from a war, didn't have a huge amount of money, was trying to economize. We have the fact that the agricultural land in the floodplain is very productive, so there was an incentive to not allow it to flood. Then you have poverty, for example, as a vulnerability. So people weren't able to protect their houses because they just didn't have money to invest in raising them up on stilts or whatever. You have the physical drivers, as I mentioned, flood, mortality, displacement, property damage. And then in this case, although there was immigration, there actually was significant improvements in levee management, and that's why there have not been major disasters in Italy anyway, similar to this since 1951. Yeah. Okay, so I sort of already mentioned that, so we'll move on to this figure from the same paper, which is pointing out more generally that this societal modulation, as we call it, often leads to more severe impacts. So what we did is we didn't allow ourselves to cherry pick at all. We took for 4 different types of extreme events: droughts, floods, tropical cyclones. heat waves, we took the most damaging, at least in money terms, events in the last 50 years, I think. And for each one, you can identify very specific factors that increased the severity of the hazard. So obviously, all of them have a physical sort of interaction component, but they also have a societal interaction component. For example, the urbanization of Houston that increased the severity of the flooding from Hurricane Harvey. Of course, the fact that the hurricane happened in the first place, right, is the headline, but the subheadline is also quite important if your house is the one that's, that's been flooded. Similarly, for most of these others, the impact storms in 2010, but also very weak infrastructure that probably would have been much more resilient. In other words, the same event would have had much different impacts if it had happened somewhere else, or if that place was an alternative universe where they had more resources, different governance, and so on. So, yeah. I won't belabor that point. But I will belabor this point, maybe. So, yeah, there's the short-term meteorology, there's the interannual variability, and there's the long-term climate change. And they all have components from different parts of the Earth system. And then if you contrast that with a very impactful compound event, I would say it's the same basic premise, but many things have to go wrong. Like in the atmosphere, say, the land, natural and human. So we have to basically be unlucky. And of course, with how complex the Earth is, and just how large it is, how many people there are, how many systems we care about, we're actually unlucky in a sense quite a lot. So this isn't an academic point, right? Like this happens all the time, that we're more unlucky than we think we might be. The one in 1,000 event, if you consider the whole range of spatiotemporal, like things across the Earth, actually happens a lot. So it's important to, I think, have this perspective. Okay, so enough with the preliminary kind of stuff. So I'll move to another example, which is Hurricane Maria, Puerto Rico from 2017. So of course there was economic stuff, there was political stuff in Puerto Rico, limiting their resources, their internal resilience. There are some reports from FEMA, for example, that because there had just been some tropical cyclones in Texas and Florida in the previous weeks, they essentially maxed out their resources FEMA had, so they didn't have much left to spare when Hurricane Maria hit Puerto Rico, and that's partly because they just hadn't anticipated probability of 3 major tropical cyclones affecting the U.S. in a relatively short period of time, even though it's not even that unlikely. So then, because the infrastructure wasn't very good, that increased the street flooding. The drains were overwhelmed, for example. Increased the power lines, and the maintenance of them contributed to the vulnerability of the power system from falling trees. I just mentioned about Hurricane Harvey, and there was also, I think, Irma in Florida that had happened 3 weeks prior. Okay, so that was that. And then there was devastating impact. So this is just an example, right, of some of the headlines from 6 years ago. And it's kind of incredible, the damage was about the entire annual gross domestic product of Puerto Rico. And the population has crashed, not crashed, but has substantially declined because the economy has, was so severely affected. Yeah, people went months without basic services, really embarrassing, frankly, for the US. So then I've just filled in, again, you can fill in every single point with a non-trivial element on this. People's behavior, the fact that it's a territory, communication, the power system, and then the rebuilding of infrastructure, whether it's the same or better, right? Like either one is a feedback. If it's better, then the feedback is positive. In other words, the impacts of a similar storm next time might be less, but maybe it's not necessarily better. there was a lot of corruption in the FEMA response process, which I put FEMA mismanagement there. So there definitely might be some sad stories if another severe hurricane hits Puerto Rico, because that'll reveal quality of what's been rebuilt. And then, of course, things like future increases in extreme precipitation act independently, as a feedback, I guess, increasing the potential hazard of a future event. Then I'll move on to a third example, California wildfires. I know there's been wildfires across Western North America lately. Focus on California. You could spend 24 hours up here, right, talking about all these different things just in the last few years. So some photos, that you've probably seen. Really severe air pollution in San Francisco, for example, in September 2020. This famous mudslide near Santa Barbara in 2018. So, there's a real loss of cultural and environmental knowledge and values that I think is an essential part of this story. So essentially the fact that indigenous people used fire as a tool and Europeans did not have any conception of the fact that fire could possibly be useful, and so heavily suppressed fires. And the graph is showing this area burned across the western U.S., I believe. And different studies have come to different conclusions, but I think this one fits at least with the sort of large fire paradigm, which is there were a lot of large fires in the early 20th century, and then by the 1930s and 40s, the U.S. had pretty much fully implemented this fire suppression policy, reduced the large fires to almost none, but then at a certain point, things become so conducive to large fires again that they start happening despite large investments to try to prevent them. And this graph only goes to 2005 or so, actually, so it's been 20 years since, really, and there's been a lot of large fires, needless to say. Yeah, and California is naturally fire prone, and just to point out here that fires are a combination, are closely associated with multivariate extremes of several sorts, obviously precipitation, high temperature, Santa Ana winds, all contribute to fire starts and extreme fire growth. Also climate change, right? I'm just not mentioning that all the time. Then, on the exposure and vulnerability side, there's been a lot of development that we have in this wildland-urban interface across the western U.S., including in California. So this is a picture. The top left one is from Colorado, so I cheated a little, but the bottom right one is from California. And, it doesn't help. Also, another sort of element of this exposure and vulnerability, exposure does not necessarily equal vulnerability. So in California, at least, a lot of the properties that are built in the wildland-urban interface, as this photo kind of suggests, are those of very wealthy people. So they're heavily exposed, but they're not really that vulnerable in the sense that they can pretty much afford to rebuild their house that's worth $10 million the next year. And unfortunately, the insurance system and so on, this gets kind of gets into governance and finance, but the insurance system and the fact that we spend taxpayer money to protect these people's houses, even though they built them in a highly fire-prone area, knowingly, it's essentially a subsidy, right, of these people making these decisions. So I think this is a case where it's pretty easy to cast blame, right, on people for doing things that affect everybody else. Anyway, so yeah, there's these really clear things we can point to that are increasing the vulnerability, not just the intensity of the fires, but the actual impacts of the fires when they happen. If we let the fires burn, then there wouldn't be nearly as much damage, right, from any individual fire. But we can't, ethically let things burn, and people just, I guess, suffer the consequences of their poor decisions a lot of the time, even if they are wealthy and should have known better. So, sort of a complicated question a lot of the time. Then there's many other things that I can kind of complain about, right, in California that are leading to people building things where they probably shouldn't be building them. Not every property that's built in a fire-prone area is is something that the person could have individually avoided, right? Like the fact that a lot of our cities have these really strict zoning codes, so people have to build on the fringe to be able to avoid anything. That's a big part of it. Anyway, so that kind of all goes in the background or setting element of the box. And then all of this leads to greater risk of severe impacts from the extremes. So I'm not really happy about this as a US taxpayer. Unfortunately, that's happening. So this phenomenon of people building things that they're pretty confident are going to be protected and that might not otherwise have happened if there weren't this sort of promise from the government or some other entity of protection is called the levee effect. And obviously it comes from levees, and this nice illustrative figure conceptually shows, right, that if there weren't a levee, people would not build important things near the river. They would they would put a park or pasture or something by the river and keep their buildings away from it. But as soon as you put up a levee and say, well, let's try to protect this land, then people say, oh, here's some protected land. Let's put valuable things there. Now, it's not always that simple, right? Because there's things like sea level rise where you have something and then the threat increases and it's not so easy to just move what you're doing. But I guess in general, I think you can make this story about a lot of our interaction as societies with the environment. We've tried to control it for the past 100 years or so, and in cases where the threats are increasing, we're, I think, recognizing that our efforts to constantly build taller and stronger are not necessarily sustainable. Yeah, so there's complex feedback loops here, and potential regime changes of both ecological and societal natures. Okay, so it's a hazardous physical driver with co-drivers like inversions that lead to severe air pollution. Some people, are talking about COVID, right, as having been one of these major co-drivers. There were times that in 2020 where people were really debating in Central California, especially, inside. If I stay inside, then I'm at greater risk of getting COVID from my family or whatever. But if I go outside, there's all this wildfire smoke. It's very hot. So it's sort of no safe place to be. At least it felt that way at this particular time in 2020 when things are going very badly in multiple ways. Luckily, things have improved since then. But of course, with extremes, it's always kind of just waiting out the clock on the next one. It's not a question of if; it's a question of when. So I guess just very broadly, right, there's these systems, they're all set up, and then there's a spark. So that describes fire weather, but it also describes everything else that I'm talking about. Then I'll provide one more final example. This one is about heat stress in South Asia. So a lot of my work has actually been on heat stress. So I suppose in a way this is closest to my heart, but it's also something I'll just present briefly because you've probably gotten the general idea of this already. I'm trying to present a very broad swath of examples of this physical societal interaction. So there's a paper from 2020 which made a lot of headlines, which found that the effect of irrigation in Pakistan and northwest India was very large. So if you know anything about wet bulb temperature, 5 degrees Celsius is a lot of is a very high, a very large difference in wet bulb temperature. It's probably similar to the difference in wet bulb temperature between, here and Mexicali in the summer. It's sort of the difference between very serious heat stress and comfortably warm, temperatures and humidity levels. So the fact that irrigation alone was increasing heat stress by that amount was really an incredible finding. And they were saying, there's been this huge increase in irrigation across the floodplains, and obviously there's enormous populations in these areas. So it kind of makes sense that under, especially in pre-monsoon conditions where it's sunny and you irrigate the land surface, then everything just evaporates into the air, and you have this enormous increase in heat stress. But then there's a paper 2 years later, also by people from India, showing that arguing that the effect was actually something like 1/10 of that size, or even less. I know this is only showing India, but you can kind of compare anyway. And what they, I think, more convincingly argued, maybe there'll be a rebuttal, but I think the right paper is closer to the truth here. What they convincingly argued is that the irrigation effect is not that large because the irrigation is happening at different times, actually, than the peak heat stress. So the people in the study on the left were using annually averaged data of different sorts, and essentially not doing it by month creates the impression that the irrigation, the peak irrigation and the peak heat stress co-occur when they actually are offset by a few months. And so the irrigation actually has a relatively small effect. And it's very easy to overlook this kind of thing, and it might sound trivial, I guess, but I think there's a lot of things in our analysis of these systems that, first of all, if you're very familiar with the system, you might think is incredibly obvious. And second, I guess that are pretty easy to overlook, maybe even if you are familiar with the system, to just ensure that your physical, science approach reflects the reality of the situation. So, yeah, I mean, I guess the fact that both teams are from India, I don't know what that says about the team on the left, but yeah, I think it just really shows these like how complex these systems are and how easy it is, I guess, to overlook crucial factors. I mean, like the implications of this are totally different. Okay, and then yeah, I guess similarly, you can actually see, this is just a side point, but I was part of this paper last year which produced this figure at the top, which shows changes in heat stress in the last 40 years or so. And you see, like immediately, without even the need for the yellow box, that generally there's been an increase in heat stress right across the world. But there's this big negative change in heat stress, and it's exactly over Afghanistan. And that's basically because, this is a quote from, I think, a UN report, or FAO report, that essentially irrigation has gone down a lot in Afghanistan because of all their geopolitical conflicts. And you can see that right from the global map. So anyway, I guess sometimes things are easier to understand than other times, sadly. All right, so now I'll move into the final part of the presentation. So there's two recent studies that I'll talk about. The first one is already published, and the other one is in preparation. So first one is more polished, and the second one is more tentative. Hopefully they'll both be interesting. The first one has a mouthful of a title. Basically, our motivation was, if you think about changes in extreme heat and changes in extreme precipitation, both of them are increasing rather dramatically, but what are the chances of multiple extremes occurring close together, whether in space or in time? And we thought a large model ensemble is a good way to do that because it physically represents things, and so doesn't rely on statistics. And when you rely on statistics for these kind of things, you can get off track pretty easily, I think, trying to extrapolate into unobserved parts of the distribution of various sorts. Yeah, so large changes in extreme events. Yeah, just a background of compound events, I guess. So the superposition, so essentially the overlapping of high impact events due to climate change. So we actually considered 4 types of things. So first, just multiple days of heavy rain in a row, which of course have their own impacts, like flooding, landslides. Multiple days of extreme heat in a row. This isn't heat stress, this is just temperature for simplicity. Of course, that has health impacts, energy impacts, can affect crops in some cases. And then 2 other things that are a little more complicated and derived from those. So changes between wet and dry years, which of course happens a lot across the western US. and northwest Mexico. And then simultaneous breadbasket failures. So essentially just taking the temperature and precipitation data on a monthly basis and comparing the, using a known relationship, an empirical relationship between heat and drought and failure. And failure is actually a bit of a misnomer. We took it from another paper. But the failure here is actually just a crop yield 25% below normal. So whether that's a failure or not, I guess depends on your point of view. But in any case, especially in more developing countries, that can lead to food insecurity, and it certainly increases crop prices. Okay, so we consider those 4 events in large ensemble, the MPI. Grand ensemble, just comparing essentially the present, so not pre-industrial. This is actually the last 30 years. So the changes maybe are smaller, right, than you might see otherwise. All 100 members of this fully coupled ensemble, we just compared it against a reanalysis. RCP 4.5 if you care, so kind of probably what will happen, for better or worse. Yeah, we considered across all these regions of the globe. Okay, so just as a reminder, so what we're looking at here is compound extreme heat. So we were looking at 3 consecutive days of temperatures above the 95th percentile and averaged over a region. So the results sort of reflect the probability of widespread high temperatures over the region, as well as the probability that heat events cluster in time. So it takes a bit of unpacking, I guess, to try to understand everything that's going on here. But I'll point out a couple things to, I guess, argue for the conclusions that I have in the bullet points on the left. So if you look at this point, if you look at Central North America, this is Central North America here. So this is essentially the Midwest of the US. The probability of having a compound extreme heat event is about 2%. So about 5% of all, because it's 95th percentile, about 5% of all days are extreme heat events. So about half, in other words, about half of the extreme heat events are compound extreme heat events. So half of all the extreme heat occurs in blocks of 3 days or more. So it's clustered together. Whereas another, and over the whole, and defined over the whole region. So it's kind of different. We went through a lot of definitions trying to get a reasonable spatiotemporal, balancing. You can see in other places, this is like Central America, right, in the 5th column. Is that showing up? Not really. Okay.
Move it to the other screen, I think.
Yeah.
Oh, there we go.
Yeah,
my bad. Yeah, I went to the other screen. Yeah, so in Central America, kind of as you might anticipate, perhaps not. It's very unlikely, actually, for widespread extreme heat to occur in general, but also in a clustered way. So there's some tropical interaction. There's some tropical regions where this is high. I think it's mostly regions that are strongly affected by. And so, for example, moving over two more to northeast Brazil and EB and northern South America, those are regions also with low variability, but very high probability of extreme heat in ENSO years. I think that's why probabilities are relatively high there. Anyway, and the reanalysis and the model, the reanalysis is the dot, and the model spread across those 100 ensemble members is in the box plot. So they agree actually very well. So that's heartening, but it is temperature, which is probably the single easiest variable to capture, right? Then, so that was over the historical period. Then you look at the changes. The changes are all positive, not surprisingly, right? There's more than a doubling of the frequency, and the largest percent changes are in the tropics. Again, not surprising. And this is, so then at the bottom, what we do is we decompose this. We decompose this change in the compound extreme heat events into a thermodynamic and a residual component. And I'll show here what sort of how we designed that decomposition. So what we have here is a probability density curve as a function of percentile. So in the historical period, that would be the curve on the left, right? And then with warming, you have a shift to the right. I mean, I guess instead of percentile, you could put just degrees Celsius as the x-axis. So you have a shift to the right, and you also have a potential change in the distribution. So if you take the historical 95th percentile as the red bar, you can see a lot more events are to the right of it. So maybe just making up some numbers, for the sake of illustration, in the current or recent past, obviously 5% of days are above the 95th percentile. In the future, it's something more. Maybe it's 12% of days. But to define a compound extreme event, what we do is we are, we're applying the definition of, we're applying the requirement, the 5% and 12% are across all days. But then we're also focusing on how many of those are in these blocks of 3 consecutive days. So that's not necessarily directly correlated, right? So maybe in the past it was 1% and the future is 4% or something, because of course at a certain point things start running together and so on and so forth. But then if you force, if you take the temporal sequence of hot and cold, if you take the temporal sequence of temperatures and increase it by the change in degrees Celsius, you get what the change in compounding would be if only thermodynamic things were being accounted for. So then the remainder of the effect is, the remainder of the compound change is due to changes in sequencing or clustering, right? So it's kind of like shifting up the distribution shifting the distribution rigidly versus shifting the distribution empirically based on the model results. So yeah, decomposing thermodynamic and residual, which basically is clustering changes. And the result for this, by the way, was that it's essentially all thermodynamic change. I know it's hard to see that, but there's essentially no change in the clustering, for temperature. Then I won't show all the results, but for those wet-dry oscillations between wet years and dry years, this is, I think, a year that's above the 90th percentile in precipitation, followed or preceded by a year that's below the 10th percentile in precipitation. So obviously this affects people who are trying to manage water or use water because they are hoping, right, generally for a smooth availability of water throughout the year, not flood, not drought. So these extremes make it hard. There's not really a regional pattern. There's not a good reanalysis result actually for all of the regions. But in the places where we do have the reanalysis is not especially good at capturing this historical probability. Nonetheless, if you look at the change then in these events, it aligns actually with other previous results, which is that there's generally an increase in the subtropics, and the probability out to the end of century, RCP 4.5, is pretty large actually, up to 50% in the likelihood of this happening. However, the changes are much less significant than for temperature or precipitation. In fact, I couldn't even bring myself to make the same kind of comparison plot as I had before. I just sort of showed the range of the models here. And yeah, showing ensemble members with a positive or negative change just to get a sense of the uncertainty. But there's a lot of uncertainty. For every region, there are ensemble members that suggest a decrease, right? So it's very hard, I think, to know what the changes will be, which I guess is kind of interesting, right? That it's defined on a pretty large scale, and yet there's still so much spread in ensemble members from a single model, right? This is a large ensemble of the same physical model. So I don't quite know what to make of that, and my colleague Laura Suarez, who is an author on this, didn't really know what to make of it either. So, models, I guess, have their challenges, but they're also the best we can do. 3 minutes, okay. So I am getting toward the end here, so I think the timing will work out well. Then the final one that I'll describe here is the Mies breadbasket failures. So I didn't show this, but the model is actually pretty good at capturing the reanalysis pattern of these breadbasket failures in the major maize growing regions, which I'll just jump to here. Is the 6 regions in these colored boxes. And so this is a kind of a weird figure, but it was intended to replicate a figure in the paper that found the empirical relationship between heat and drought and breadbasket failure. So they had a figure like this to kind of show, again, because the uncertainties were kind of weird, they, I guess, thought it was the most insightful to show this change in probability as a box plot for the most common result of the number of regions that are simultaneously experiencing breadbasket failures in the same growing season. So the most likely the point of all this is that the most likely outcome of a number of breadbasket failures, occurring simultaneously from the past to the future increases from 2 to 3. Okay, and then and that's the sort of lighter red and the darker red boxes, and then the smaller box plots are just a total theoretical exercise, but we were curious because the discussion around breadbasket failures hadn't really incorporated before, well, what if people managed to, through breeding or other things, adapt the crops a bit? So we just did 2 other theoretical exercises where we applied the same definition to our results, but increased the temperature and decreased the precipitation thresholds at which failure was assumed to occur, or has occurred, empirically from the data. And so that more or less reduce, like if we could increase the temperature tolerance of corn, maize by 1 degree Celsius and its tolerance of total precipitation by 10%, that would essentially adapt corn perfectly to the future. But if we don't, then the risk of 3 or more of these 6 major regions experiencing failure conditions simultaneously will double. There's, sort of hope and realism mixed in there. Okay, so I'll kind of just skip this. This is you can ask about that later, but we're trying to understand the risk of different regions failing simultaneously. Okay, so why this matters, right? I guess having the large ensemble and the global scope, I think, helps us sharpen our ability to understand particular tail end risks and to assess, which regions maybe are worthy of understanding the dynamics of more carefully. And then I'll very quickly talk about the final study that is being conducted in this physical societal framework, although focusing again on physical things. So it's the heightened risk of heat stress near tropical cyclones. Just an image from a TV report, and it's showing the heat potential, so based on the SSTs. But, and we know tropical cyclones are destructive, but, we know extreme heat stress often occurs at the same latitudes and in some of the same places as tropical cyclones. So our question was, well, are they physically connected in any way? And if they are, then that has really serious implications for people trying to prepare. For example, there's been some well-reported issues in the U.S. in the last few years with power outages in the wake of tropical cyclones, and the fact that people who depend on power, to stay cool, for example, our senior citizens in Florida, they often have health conditions and so on. The power goes out for a week. That's a really major health impact for them. So, correlated risk. Okay. So we took. Not sure why it's skipping there. Okay. So basically, we just defined heat stress, and we had a pretty strict definition for this interaction. So we're looking at 95th percentile heat stress that occurs within 24 hours and 500 kilometers of the center of a hurricane-strength tropical cyclone. So you can imagine that tropical cyclone actually has larger impacts than that. There's many impacts from weaker ones, but we're just taking the most strict definition to prove the point, I guess. So think of it as if there is a tropical cyclone nearby a point, what is the risk of heat stress in that place? And in fact, if you forget about the 95th percentile and just look at the all-time maximum heat stress near a tropical cyclone, you actually get a fair number of points, most of them across the ocean, but some islands and so on, that show up. And you can even see the tracks of individual cyclones here. This is from Igor. So these are points that had the all-time maximum heat stress in association with Igor. And you can see day by day, even in 2010, as Igor went along in the dots, all those points in the ocean had their highest ever heat stress right as Igor was going by. I think this is pretty cool. And then this one is the risk definition I was talking about a second ago. So conditions on a tropical cyclone being nearby, what is the risk of heat stress? And of course, I'm not, we're still exploring this. This is the one that we haven't even submitted yet. So there's some negative relative, or less than one relative risks, which I'm not totally sure about. But in most of the areas where you can define this, where the sample size is large enough, the relative risk is positive, and it's often like 3 times or more, including over a lot of the Caribbean, Hawaii, parts of Australia, South Asia, and so on. And on top of that, this might even be an underestimate because it's only hurricane strength storms. There's not extratropical transitions and that kind of thing. So I think there's a lot more to do here. Just about the only things that we've done really are we're working on parcel tracking approaches right now. But if you just composite over the ocean, you kind of see the patterns of this is moist static energy, heat stress on the left, temperature, specific humidity, and omega, vertical motion at 700 millibars. And then the top row is the tropics, subtropics, and mid-latitude. So yeah, there's some interesting stuff that I'd be happy to talk about with ocean experts. And I know this is only at 1,000 millibars, so the information, except for the vertical motion. So the information might be quite different if you look at 500 millibars. Anyway, so we're just trying to get a rough sense of it right now. And then if you look at kind of the time series, you can just see that it happens over 2 or 3 days. Generally, if the heat stress goes up from somewhere near the median to the 80th, 90th percentile as the hurricane or the tropical cyclone passes. And this is from weather stations, so it's not just like model data. Anyway, so they're closely linked. We want to partition this into like advective versus diabatic components, especially. Yeah. So the joint conclusion of all of this, I think, better subdaily data in a lot of places is really important. The societal uncertainties, which we often think of as like you could call state variables, things kind of are what they are, but I think it's more compelling to talk about the vectors, how things might change or are changing. And then, more multidisciplinary work is always important, but I try to at least practice it in some of my work. So it's a real data and methodological challenge, but I think what I try to encourage everyone to do, and I say it, for my own benefit, right, also is, really trying to account for this whole chain before you reach a major decision. So a lot of times people just focus on one box or another according to their strengths, but if we forget about the rest of the chain, a lot of what we do won't be as meaningful. So I think, like for us as scientists, it's really being aware of where things come from, how they might be used, sort of as necessarily actively soliciting information about the different parts of it, which may not be as well characterized or so on as we might like. And then often a lot of things that we think about in terms of, say, risks in a particular region need to be re-examined due to climate change or in light of the information that we might get from soliciting information about these different links in the chain that are intimately connected with each other. That is my final slide. Thank you.
Thank you, Colin, for your presentation. Very interesting, and it seems like these societal variables are very complex to include, because how do we quantify that influence, which can make difficult to analyze. Let's start with some questions here in the audience. Anyone? Well, in the meantime, I have I have a comment on the oops. And the story that you use the different IPCC regions and to see the heat stress and the future changes. We have, I'm working with some Latin American people to do the adaptation and the challenges of adaptation in Latin America and the Caribbean. And one of the things that we see is that these huge IPCC regions are too big. Yeah. And sometimes the results are misleading because you are averaging this large domain that maybe cancel out the real impacts or the real observations. I understand that your story, the story that you show is global, and the IPCC results also are global, so they have to average in some way to summarize the information. But at a regional scale, we always look at going down in the scale. Do you have any comment on that?
Yeah, that's a great point. And I'm a big, maybe that study is a little misleading in terms of my interests, because I am really passionate about regional factors and the fact that a lot of global studies necessarily or not necessarily perhaps overlook important regional things. And I think it would be great to come up with, I'm not sure if this exists exactly, but to come up with a way of naturally delineating regions, because in some places like the Midwest US, right, you can actually have a pretty large domain that's meaningful. But in somewhere like the Caribbean, I mean, like the windward and the leeward sides of the island can have quite different vulnerabilities to drought or something. So it would be more meaningful, I guess, to have a region that maybe consists of like the windward sides of the islands and another that consists of the leeward sides of the islands. But it would have to be very carefully designed with regional experts to make that as effective as it could be.
Yeah. In your last analysis of heat stress from the tropical cyclones, that's very interesting. So that has some predictability potential.
That's our hope, yeah, that it can be used to better anticipate heat stress along the coastlines and islands.
Any question?
And, well, I was just going to say, and it's connected with the SSTs, obviously. So,
the what?
With the SSTs.
The SSTs.
Yes.
Okay. And actually, from the other story that you showed, in Mexico we have many examples of those compound societal events, and it's very interesting because sometimes there is this misleading idea that tropical cyclones are the main event that produce hazards or disasters, but sometimes we just need the passage even of a weak tropical cyclone to produce a disaster. And we have some examples in Tabasco, in southern Mexico, and it is just this accumulation of different systems during the season that gets all these different factors, and then boom, we have a disaster. So it is interesting and complicated to analyze that.
Yeah, I think I had it in one of the slides, and I kind of glanced over it, but I believe that you could almost say that no disaster is really natural now that we know so much about, we have such complicated societies, and yeah, our fingerprints are all over the world, and you can't really say anything is natural, and everything is dependent, I think, on the system that's being impacted, as well as the hazard itself. I mean, like the Texas cold spell, right? The kind of cold event happens all the time in Canada or Minnesota, but they purposely were not preparing, or they were choosing not to invest sufficiently in protecting their infrastructure, and then they had freezing water pipelines and burst natural gas pipelines and that kind of thing, and then everything kind of followed from that.
Yes,
it's a very relativistic view. In other words, the frequency of the hazard.
Exactly. See, many of these hydrometeorological disasters are constructed. Part is natural, but a large part is constructed by society. Yeah. There was a question somewhere? Yes.
Yeah. Okay. You can take a look to the news from Puerto Vallarta, news from yesterday regarding degraded cyclones. No, what they can do.
I didn't follow that, but I did see the cyclone had made landfall. I didn't read about it, but
it was quite heavy.
Sounds like I better.
But just another very general question regarding your procedures. How do you deal with this the problem of the point of using 100 models? I mean, at what point are you really gaining information, or how do you say, what's the difference between using 50 or 100? I mean, are you really improving things when you have 100 instead of 20 or 50? Or, and the other thing is related with is that if you are not losing also information because you don't know who to blame, what model to blame for the physical mechanisms that are behind the final results.
Yeah, that's a good point. So just to emphasize, so that's a large ensemble, which is the same model, just run 100 times. So I guess it's essentially an alternative to a statistical approach. And I think to the extent that the width of the ensemble output is something that might reasonably happen. And I guess everything kind of depends on what you consider to be a reasonably large risk that we should be concerned about. If something is 1 in a million, I think we can probably agree it's, not really worth the fact that, a meteor would destroy this building or something. Right? It's not really something that's within our realm of consideration, but I guess as you go up the scale of socioeconomic, or let's say economic value, you tend to become, I think, concerned naturally about more and more infinitesimal risks. And so I guess to the extent that the ensemble is still telling you about something that has a probability of happening that's within your field of view, then I think there is value. And then also you can get more physical, in the case where it is different physical models, but also I suppose in the case where it is the same model replicated 100 times or something, you can then pursue this approach called ensemble boosting, where you can zero in on an extreme event, and then you really have the preconditions because you have run a physical model. You know the exact preconditions that led to that extreme event, and then you can kind of target your efforts to say, okay, these are the kind of preconditions that lead to a really severe event. Let's start the model. The ensemble boosting approach is let's start this model or other models again with these exact preconditions, and then sort of very efficiently get a spread of output around that extreme event, and inevitably you get events that are even more severe than the single realization that you had from the one member of the ensemble. So this has been shown, I guess, this has made a big splash when it came out in climate science a couple of years ago, and I think has a lot of potential to really explore the physical mechanisms of extremes in more detail.
Okay, so yeah, then for a single model, then you have the issue of the internal variability or something like that, no?
Yeah, there's always, I know, I don't know how to answer that, but it's like most studies, just about every study uses either an ensemble of different models, usually one realization of each, or 100 or 50 realizations of the same model. And I guess it would be great to have a large ensemble of every model, but then, then you go back to the question you just asked of, well, is this overkill? And I guess that's something that, people need to figure out as a community for particular events and so on. Yeah. Some guidance from the IPCC or something, I think, would be helpful there.
And also it's very expensive to have many ensembles. So.
Exactly.
Thank you, Colin. I just wanted to ask, well, actually, one of the things that I wanted to, I was thinking about now that Luis mentioned the large ensembles, there is now these multimodal large ensembles. And actually, that's the idea. Because when you have just one single model, indeed, your error is mixed with the internal variability. So there is no way of separating those two. But that's why, they designed these new large ensembles, because now you can actually quantify the internal variability on its own. And you know that, the differences that you get are actually due to the climate, the dynamics within the model, and not the differences in the configurations of the models. But then now I think some centers are intending to do these multimodal large ensembles, which is trying to tackle these both problems at once, which is, of course, you have to deal with a lot of data, but that's something people are starting to do. But I wanted to ask you one thing about when you say that you separated I think it was for your definition of heat stress, that you separated somehow the dynamic from something that you call the residual, that I don't know if that's the dynamic part. How did you manage to do that?
Well, it was a pretty simple approach, I guess, but we kind of went back and forth and decided this was the best because, you're often weighing the complexity of an approach versus its value. We decided the simplest possible approach that we felt could reasonably decompose thermodynamic from dynamic or residual effects would be the one that seemed most appropriate. So we just took, if you picture the time series of the temperatures, we have that for the historical, the current model simulations and the future model simulations. And so each of those has an inherent temporal clustering that you can define, if you impose a particular threshold of heat stress on that time series. But then if you picture taking that time series and increasing it by the mean change at each percentile, you can sort of create a synthetic future where the clustering approach, the clustering effects that are baked into the future model simulations have been more or less removed. And I think there are other ways that this could have been done, but we felt like this was reasonably defensible. And we didn't just apply a single temperature delta. We did the 95th the 90th percentile increased by 3 degrees, and the 99th percentile increased by 4 degrees, and so we applied all this to our synthetic time series to try to estimate, a future without changes in sequencing. And for temperature, we didn't really find any change in sequencing at all, which kind of makes sense. For precipitation, we did actually find some, but I just didn't include it because it's something like 20% of the increase in future compound extreme precipitation is due to greater clustering of extreme precipitation days together.
And you find that it's the case for for all of the global regions that you analyze, or the regional?
No, there are some regions with decreases as well.
Okay.
But generally, the extreme, maybe I should have included it as an extra slide. The extreme precipitation generally actually does increase in most of the world, which kind of makes sense because of Clapeyron relationships. And I guess the flooding they just had in Libya maybe is indicative of the fact that just because a region is decreasing in precipitation doesn't mean that it's extreme precipitation, especially multiple days of extreme precipitation, might go down, might go up instead.
Yeah, I was thinking about that case when you explained all that, because we saw this very important impacts on. It was not only just because you had a very strong, weather event, but also because of the structural damages that you had in Libya.
I think. It's an incredibly powerful compound event, because it is so tied to the political and economic situation there.
Yeah. Thank you.
Bueno, ¿hay alguna pregunta en Facebook o en Blue Jeans? ¿Hay alguna pregunta en Blue Jeans? Parece que no. Okay. So if there are no more questions, well, I have few, but we can talk it over the queso, pan y vino. Okay. Pues muchísimas gracias. Thank you very much, Colin.
Gracias.
The broadcast of Facebook Live has stopped.